Hello, HTEC educators. Welcome to the 2021 CNC Project Elevator Pitch Session at the HTEC National Conference. This year, the HTEC Council has created a brand new CNC project session. Since we're virtual, we've created our poster project session and we've converted it into a virtual elevator pitch project session. So join me over the next 35 minutes in watching 9 different projects that our CNC educators from around the country have submitted to showcase to you. Now, the cool part is everybody who's submitted a project is willing to share their material with you if you would like to maybe use a part of the project in your classes on your teaching Haas CNC machining. So the format of this is it's random order. I pretty much took the videos, inserted them random order in here, so all 9 videos. And at the beginning of every presentation, there's going to be a title and who's actually presenting. Now, the educators have been asked to provide their contact information at the end of their presentation so you can go ahead and contact them if you're interested in learning more about their projects. So let's check out these 9 exciting projects. Here we go.
Hey, hi, my name is Antonio Espinoza, and I'm going to talk to you about the speed handles that we did on the CNC mill. These handles are used for a vise, either on a manual or on a CNC mill. So the software we used for this was Fusion 360. This was my first time using this software, but my professor provided us with YouTube videos on how to make basic drawings or basic dimensions, and this wasn't that hard. So we each had different tool paths, meaning that we each had like a different start and a different finish in order for us to have like a different and unique code. So for example, I could have started making my holes first on my part. Someone else could have started shaving off, excess material. So for handle side one, we took off most of the material in one shot, holding on by the vise. Usually it took us about like half an hour to get the side done. For side two, we had the part flipped and it was held onto by these handle jaws, which was made by the first 2 people that finished the project. And this only took like 7 minutes because it was just facing down the excess material at the bottom of the part.
Hi, my name is Michael Grader. I also helped with the project. We used like the CNC machine to like all 4 tool slots to help make some like CNC cranks. This is like a crank I designed in the like Fusion for like how like we made things. This is just like the basic crank for like competition and all that we use. We then anodized some of these cranks and handed them out to our advisory board members as a thank you because some companies help supply us for the school and all that. We used a bunch of materials we used for the tool slots in the CNC machine that we changed. Used screws and all that, hex keys, tightening and all that. And then this is the link for the blueprint for the machine. So if you want to like design it yourself in Fusion, and this is the videos on how to do so if you ever want to.
Hello, my name is Franz Weitschegger. I'm with Sierra College in Rockland, California. This is Advanced Manufacturing, Machining Level 1. There are no prereqs for this class. This is my connecting rod bottle opener project. This is the finished project, and let's hop into it. So this is my lab at Sierra College. We have 9 Haas VF1s, very fortunate. I provide the students prints. Each one of these prints are the print is broken down into 3 prints to make it a little bit easier for these entry-level students to understand what is going on. With each print, I also provide a screencast video link. And so it goes through here, I reference my prints, and then I go through and show them how to model it inside of Fusion to help them when they are not in the classroom. And this is just a link to the screencast video. This is the modeled connecting rod. This is a CAD inside of Fusion. We also go through, I provide, again, entry level, so I kind of spoon feed them how to set this up in CAM. So I created all these instructions in Word docs. I did all screenshots of how to create it, examples of the tool path after you've completed it. And my saving grace in this class is after they've completed the tool path, I have them create a setup sheet again in Fusion 360. In this setup sheet, I have the important parameters. So Z minimum, max RPM, max feed rate, which it's just saved me a ton. And so the students will go through and they'll verify operation by operation to my master copy, which is what you see right here. And if there's any problems, they bring it to class and we fix it in class. So here we go. Let's go. So before they run the machine, I have these checklists, and so they even look at the coolant concentration, weigh lube level. They got to check their stock size, write down their tool numbers, do a quick description, verify their XY location, 5%, coolant off, let the cutter engage in the material before they let the coolant rip so they can make sure they're in the right location. This is roughed out. This is the very first one. So they first use that corner, and then, oopsie, we machined that corner away. So then we come back to class and lab the next week. The only finished part was that bore. So then we got to figure out, we got to use our mechanical edge finder, locate that bore, or an indicator, locate that bore, move our WCS inside Fusion, and then finish the detail inside of here. So that's real neat. Here we go. That's just inside Fusion, the CAM environment, tool pass. They post the tool pass they want to post. This is the finished top side of one. So then how the heck do we machine the back side of this thing? Because we have a square and we have this weird shape. So we show them how to, inside Fusion, we create soft jaws using the part geometry to project onto the soft jaws, cut, create them, machine them. We use these as our multi-use soft jaws. These are machined in class, students, I mean, there we go. So we also model it, use the joints, put them together. Our known location is right here. So we touch off there. Our Z is the bottom of the pocket. This is a finished part from a student. Again, all these are student parts. Student part, oh wait, we're not done. We have inspection. So at the end, I have a Form 3. I created this document. I have these reference numbers, a characteristics number, and they measure them. And I kind of tell them what tooling or instruments to use, height gauge, mics, gauge blocks, gauge pins. And they go through, they inspect the part, they see how good or bad they are, and it's an awesome project. Students really like it. They can connect from what they're doing in class to the real world because they walk away with this little kind of a keychain bottle opener. So that's it, Sierra College. Thanks a lot for your time, and have a good one.
All right, ladies and gentlemen, this is our business card case. This was done, so it's not a particularly sophisticated item. It's a rectangular box, holds a series of business cards that you can just slip out one at a time. Neat little project, nothing fancy. The idea behind this was we set this up in conjunction with the Streamwood Career Exploration Program, which is something the village of Streamwood, the city we live in, runs an event every year that allows us to tour local facilities, to tour local manufacturing, as well as participate in a production run assignment. So the CAD, the CAM, and the design was before spring break, and then the actual production run occurred during spring break. So here it is. Basically, it's got a rectangular hole on one side. You just thumb the cards out one at a time. We did actually in 2018 hand off some of these with the Gene Haas Foundation logos to the Haas Foundation just as a thank you, because they got our back. We might as well give them some neat stuff when we make it. We started this in 2018, carried it over to 19, and then 2020 we were supposed to do it, but obviously COVID got in the way. Village of Streamwood runs this, and basically the idea is we take over the whole shop, we run all the equipment, and try to do a production run of something. Most students only do individual projects, so it's kind of fun to get them to think outside the box a little bit when we have to consider making many of something. So this was fixtured in a custom setup, Mighty Byte holding fixture type rig. So here's the CAD model of how we did it. Basically, this is maxing out a Haas mini mill. It's about as big as it can go. There's 3 parts. 2 of them are billet aluminum, and then there's a piece of spring steel that gets just a simple shape applied to it, and then 2 screws go through there, obviously through these holes, and pinch the whole thing together, hold it in place. Pretty simple, pretty elegant. It actually works quite well. The fixturing, it was all multi, all like Mighty Byte type fixtures. You've got the the spring here. We're hoping to, as part of process improvement, create a one-hit stamping die so that we can actually just make these things in an automated capacity instead of shaping them by hand. And then it's also our hope to possibly anodize these. so that we can, when we do the laser engraving, obviously it pops a little bit better. And then there's Real World Scholars and Harbor Freight Ed Corp. And we're looking to maybe tie in with those and maybe sell some as well. None of this is official. Obviously, we need to get back in the swing of live students before we can take on this project again. If you'd like to see this project or want to know about this project, email me, matterbach at u-46.org, and I can give you the links. I've got the 3D solids, I've got the basic prints, etc. So let me know if you got questions, and yeah, take care. Morning, ladies and gentlemen. My name is Matt Erbach. I'm presenting the Streamwood High School ID holder. The idea is pretty simple. We incorporated this idea in the senior class, designing the tooling, the fixturing, the processes, the CAD, the CAM, and it's intended to be used in the lowest level students, so my freshmen and my sophomores. The idea is it's a turnkey, ready platform so that the students will they're not. They won't have to get into the specifics of like touching off tools. They can do this very, very early in their school experience, so that they might not have a lot of skills yet as a freshman, but they can still hit the cycle start and monitor a job and load and unload and things like that, and produce something that looks pretty good that will serve two purposes. Number one, it'll help promote the program, and number two, the idea behind this is everyone in my school is required to wear their ID on them at all times. So they've got these typical traditional sort of lanyard with, the ID hanging underneath, and they're a huge safety hazard in the shop. So the advantage with this being equipped with a belt clip means that the students can clip it to like the pocket of their jeans, and they're still meeting the district expectation of wearing their ID, but it's not around their neck where, they're potentially going to hazard themselves. Two parts. You got the clip here, and you've got the body of the ID holder, some screws, and then the acrylic needs to be either laser cut or run on like a table saw, and then just corners radius to fit, filleted to fit. So I did this with my seniors, and they did the tooling, the CAD, the CAM, pretty much as we could possibly arrange. So you can see here that what we've got is multiple holds. Hold one is up here. I didn't have much room for it. Takes a 3-inch bar down to size on the edges and does as much of the drilling and tapping ops as you can. Hold 2 obviously locates on a couple of fixtures here, little mighty bite holders here, and that gives you all your corners rounded down and your big internal pocket done. And then hold 3 is just essentially a backside chamfer. And then you can see here we've got a similar multi-stage process. You'll notice that everything's going in pairs. It's going in pairs because I want the student to produce one for themselves, and then I get one as well to hand out to a staffer at the end of this. You can see here the results. Obviously, this is a completed ID holder. My apologies. That was the only photo, only one I had available to do this with. But you can see some of the parts here the students have produced. Your materials list. Future work. The assembly screws are currently 440s. I want to go bigger. I want to tweak the belt clip a little bit. It's not quite as good as it should be. It's a little bit too rigid, so it's very difficult to clip into your pants. And that's basically what's got going on. If you want to know about this project, matterbach at u46.org is where you go. Send me an email, and I'd be happy to hand you the prints, the solids, and everything else I've got on this, because it works well for me, and it might work well for you. Take care.
Hello, my name is Treon Giorgio, and I'm going to go ahead and explain my live tooling lathe part for my IME 336 course. IME 336 course is a junior level manufacturing engineering course offered at Cal Poly, and it's the second CNC course that the manufacturing engineers take. It's focused on live tooling, multi-axis machining, CNC macro programming, and advanced CNC concepts. So what we do in this class is we teach manufacturing engineers all about live tooling CNC lathes. So that's what this project's really dedicated to do. As you can see, the engineering drawing's right there. And this part has a -12 AN fitting with a 1 1/4 inch hex on the side that gets cut with a live tooling lathe with a 3/8 inch end mill. Now, we then have the other side have a PEX fitting and a large bore where the students are basically learning how to use boring bars for the first time in this project. Now the students are only given this engineering drawing like you see right here. From that engineering drawing, they have to go ahead and figure out how they're going to produce that part through all the different operations. They have to figure out how they go from raw stock to finished part. So as a class, we do some production planning, and we come up with a stock size of like 2 inch by 4 1/4. We figure out how we're going to hold it. So in this case, we're using a 1.975 board soft jaw that's 1.375 deep, and it holds both operations in that same soft jaw, as you can see right there. So that first CNC operation, they go ahead and they used Fusion 360 in this project. They used both Mastercam and Fusion 360 in this course. So this one was a Fusion 360 project where they machined that -12AN fitting all the way up through that to the back of that 1.975 diameter. So they learned facing, turning, threading, spot drilling, and axial live tooling. And we ended up chamfering that part with a bull nose end mill, a 3/8 inch bull nose end mill, and did a little 3-axis machining. Now, thanks to Tim Paul from Autodesk for coming up with that idea. Now, the part is going to be held in the same soft jaw bore for the second operation. So they machine that PEX fitting side, and then they do the large bore machining for that second operation. And so they're facing, turning, spot drilling, and boring. The reason we had to drill twice is we don't have enough Z right there. We had to get a stub drill. So to hold this, to machine this part, we needed a soft jaw set. It can be done in an 8-inch or 10-inch 3-jaw chuck. Mine actually happens to be a 10-inch 3-jaw chuck. So I have an ST20Y with the BMT turret right here. So you can see that behind me. And the tooling for this project is in terms of cutting tools, you can get it done with a CNMG, a BNMG, and then some sort of OD threading tool to do that 1 1/16 inch -12 thread. You need a 3/4 inch, 120-degree spot drill, a high-speed steel 5/8 inch stub drill, small boring bar, and a 3/8 inch bull end mill with a 15 thou radius. And I'd like to thank SwiftCarb for donating the end mills for this project. Thank you. Now, you can see, so the students go from solid model to finished part just from an engineering drawing. And at the end, they use the metrology lab to go ahead and validate their process. So they measure the part using the optical comparator to validate that they machine that PEX fitting correctly. So again, I'd like to thank Fusion 360 and SwiftCarb for their assistance on this project. And if you have any questions, you can contact me at tgiorgio@calpoly.edu. But this is my live tooling lathe project from IME 336 at Cal Poly. Hopefully you've enjoyed this project. Have a great day.
Hello, I'm Phil Shirley. I'm with Georgia Northwestern Technical College. Welcome. I'm part of the HTEC Planning Committee. I'd like to extend a special thank you to all the other members. They have done an outstanding job through this entire year. I've been very blessed to be a part of that. I also look forward to seeing everybody in person before I get into my project. This is not quite as polished as Treon's, I'm sure, but hopefully it'll go well and you'll learn a little bit of something. I'm doing a classic project you might have heard and seen. It is the Turner's Cube, and it is time honored. I think many programs and machinists have used this over the years, and I'm doing a little differently, and hopefully this will be something you would enjoy. There it went, finally. Okay, my computer's a little slow, and you'll have to forgive me for that. Turner's Cube project is been around for a long time. We're using a 5-axis. We're doing this with 3+2 machining, manual G&M coding, speeds, and CAN cycles, of course, multi-fixture offsets, subroutines, and CAD/CAM programming. We're actually doing the project twice. On the first project we do 2 orders of operations. We cut 5 sides in the first op and then finish it when the sixth side on op 2. With all the parts and pieces there, we manually G-code for cutter comps and rounding and some of the other parts of the project, and later go back and program it complete with Fusion. Students will learn a lot of other things in there, subroutines and manipulating the code and that sort of thing. On op 1, they get a drawing like so, and they will actually generate this drawing in class. So finish top 5 sides complete, You see that? That's as it's finished using A and C axis, and then the A operation 2, they'll finish the 6th side, and you'll have to use spacers in this, and we'll show you right here the total machine time not to exceed 16 minutes and 45 seconds. So obviously speeds and feeds are important, and not forgetting anything, of course. We also do something different. We use a small Woodruff key cutter, slot cutter, to cut the corners and relieve the corners, so that we cut the block on the 6th side, the last off, then the cubes will all be free when they leave. That's why we need the spacers to keep them bouncing around. And if you don't use the spacer, Mr. Bill says, I won't do it. But if you get this joke, you're probably old. So anyway, there's the finished cube. Your complete project can be found on YouTube. You search for GNTC, Turner's Cube, and links in the description. That will include the Fusion file, the G-code program, the setup sheet tool list, and also I'll put a link to a tour of my shop on there. Hopefully that will be something you'll enjoy. And I think that got it. And thank you for watching. I hope you enjoy the conference. It's been a big deal, you know, and look forward to obviously next year meeting with everybody. Have a great day.
My name's Adam, and this is Cole, and this is why our fixture design is the best for this project. The task at hand is to design, manufacture, and test a CNC milling fixture that will be implemented onto an FMS pallet system on a Haas EC400 horizontal CNC mill. The fixture needs to hold the OP1 keychain blank and allow the CNC machine to perform the OP2 milling procedure. The fixture must be designed, built, and tested utilizing Mike 6 tooling plate, Mighty Bite fixture supplies, SolidWorks, HSM Works, and the Haas CNC VF2 Super Speed mill. The overall goal is to multiply this fixture and scale up mass production of many keychain parts on multiple tombstones in the pallet pool of the horizontal mill. Design constraints and criteria for this fixture design consist of a few main things. If achieved at a minimum and ideally exceeded, the design of the fixture should be successful. This includes producing 2 finished keychain parts and the clamping forces of the fixture withstanding the tooling forces with a minimum safety factor of 2.0.
To meet the design constraints mentioned by Adam, we locate our part face down on the tooling plate, butted up against a 2-inch Mighty Bite locating rail, and lastly pressed to a 0.375-inch dowel pin. The part is securely clamped against the B datum with 2 800-pound Mighty Bite clamps, which are centered on the individual keychains. A WCS bore is in the top left to be conveniently probed, and a 0.25-inch pokey yoke dowel pin was added to prevent improper loading. The last features present are a square indicating band, 2 T-bracket bolt holes with excessive counterbore relief to mount to the fixture, some cosmetic engraving, and chamfering for comfort. To ensure our keychain parts would not throw during milling, we found that we needed a minimum of 28 pounds of clamping force when roughing with the 1/4-inch end mill and 40 pounds during the face milling operation. To verify our keychains would not deform, we conducted a finite element analysis to find an approximate deformation of 3 thou at the 800-pound maximum clamping force, along with a passing von Mises stress. The deformation amount we found was insignificant and unnoticeable. Next, we'll take a look at the assembly drawing, the exploded view drawing, the fixture plate drawing, and notice the 3 datums, A, B, and C, along with the tight rail slot tolerance, which we will need to meet by accounting for tool wear. Then we have the standard parts drawing, a picture of the empty plate, a picture of the assembled plate with a loaded part, and lastly, an animation of the exploded view. Our operation planning document is presented above. We used a WCS of the bottom center of the stock and utilized the pre-made tooling library to design our cam, obtaining an approximate operating time of 22 minutes, which we'll conservatively call 40 minutes. This operation simulation shows contouring of the sides and indicating band, pocketing of the clamp relief, rail slot, and WCS, spot drilling, reaming, and tapping. Believe it or not, reaming before drilling will break a tool, so don't learn by doing that. Lastly, we engraved and chamfered. These pictures show our fixture post-operation. Everything went as planned, fits securely, and produces beautiful parts.
As for the economic feasibility of our fixture, the design proved to be more than reasonable. Costing analysis of the fixture can be seen here with the total estimated fixture tooling cost of about $1,600. If you notice, engineering costs are what make up the vast majority of this number. With these numbers being conservative estimates of our completed work, it can be said that this cost could in fact be far less if completed rapidly at the convenience of the buyer. Altogether though, the design is economically sound and repeatable with the ability to be produced multiple times for the tombstone. In conclusion, why should you go with us? Our fixture design is successful in many ways, meeting all design criteria. However, places it exceeds are with the load-unload time being well under a minute with simply using a torque wrench. Furthermore, our extremely ergonomic design includes features such as the poke-yoke dowel pin, easy to understand datum locating features, and the G54 probing bore. The design is cost-effective and easily machinable with carefully selected supplies that are available and as inexpensive as possible. No features are redundant. It is extremely user-friendly and allows for the creation of many parts effectively. Lastly, the overall goal of producing quality parts to spec is met and verified with great assurance.
Hello, I am Ed Doherty from Suncoast Technical College in sunny Sarasota, Florida. We're part of the Sarasota County School System, and I am Ed Doherty, the 8th year instructor here at STC. We're talking about automation, Haas CNC lathes, and UR robot collaboration, loading and unloading. How can we learn to work with automation? We have 2 high school programs here at STC. In my classroom is a CNC specialist, and next door is advanced manufacturing. We also teach adults in our 1-year machining technologies program, which is also me teaching that one. In advanced manufacturing, they have a UR5 universal robot, and they've had it for a couple of years, and we have 3 Haas CNC machines, a VF2, a TM1P, and a ST10 lathe. HTEC 2019, I attended the conference in Kalispell, Montana at Flathead Valley Community College. VersaBuilt did a presentation. Al Youngworth from that company talked about robot to CNC integration. When we got back, we decided to get the UR robot connected to our Haas machine. We bought a VersaBuilt kit with a legacy control. We also selected the lathe because it already had a programmable chuck, and we'd already seen some other videos that it was possible. Up in the upper left corner is one of the YouTube video clips we used to watch. We brought over the UR5 that was on a training platform already with a gripper. We figured out it was capable of loading and unloading. We installed the VersaBuilt kit, learned a lot there, and then we picked a CNC project. We did a modified Fusion 360 Design Academy course in the lathe area, and it was about 2 inches in diameter. Okay, we got our high school students working in there. There's a lot of them going on to engineering or into manufacturing, but learning how to solve problems and actually make things at the same time. This is our lathe part here. We have our setup sheet here. We cut soft jaws 2 inches diameter by 750 deep. The material was 2 inches diameter by 3 inch long. Typical roughing, finishing, grooving, and parting tool, but we did not part it off all the way as we wanted the robot to unload it. We did add a G72 cycle for some of the oversized lengths, and I'll talk about that a little later. All right, here's our robot. We made sure it worked and we could be set it up and clamped in place easily. And it already had the gripper, and pretty much all the students had learned how to use the robot through the UR Academy online. This is the VersaBuilt kit. There's Al up in the top there. On the left is the add-on software, the VersaBuilt supplies that you put into the UR pendant. And on the right is part of the kit that we had to install. Let me just move my person over here. You get a little box there and some RS-232 cable, a cycle start cable, little power cable, and what else do we have? Ethernet pendant to the UR. All right, next would be, ready, set, go. Our Tampa Bay Buccaneer Championship flag in the back, but we did a couple of tests with make sure it actually worked loading, unloading, and worked load, make the part and unload. So in the end we had success. We used a little chute on the left that Tom had designed and could pick parts out of the chute, load them and unload them and just drop them in the box for a quick setup. On the right is Mr. Lasorso, who teaches the advanced manufacturing class, along with Thomas, who came through that class. So it was a good project. for many reasons, how to be current or ahead of the curve in manufacturing, good for engineers and machinists, and a good problem solving, planned and unplanned. Unplanned was some of the material was oversized and wasn't loading quite correctly, and we were trying to machine off the face like a 1/4 inch, and one of the parts came flying out. So we added a G72 cycle to pre-machine, and we also added a spring-loaded plunger to have the turret push the parts in so they make sure they were seated in correctly. And also look at the future for everybody. Even the full-time machinists could see what was coming down the road for machining. Okay, that's it for me from Sarasota, Florida. Ed Doherty, see you next year. Howdy out there, this is Ed Doherty at Suncoast Technical College in Sarasota, Florida. And we're part of the Sarasota County School System. I am Ed Doherty, and I'm the 8th year instructor here at Suncoast Technical College. Okay, first impressions. Our county bought 2 of these machines, and they were meant to go to high schools engineering programs. We have 6 Techno Da Vinci roll-around similar machines to this that are laptop-based controls, and they're pretty much dedicated to only one project. It was called the TSA CO2 Dragster project. So they wanted to get into a better like tabletop machine. It wasn't as big, and they looked at some other brands and decided to try out the Haas because of our success using Haas machines in our technical school. And I've been working with everybody on the CO2 dragsters, so I'm kind of familiar with the CTE instructors. Plus, I realize it's not really a machine for our lab, but we want to be able to teach people how to make things, and not just additive manufacturing, but subtractive manufacturing, and also if they have an interest, they can end up in our lab and continue to learn. And this would be good for us because it'd be like pre-training. Okay, so we had to do some little bit of like what's what on the machine. We realized it's ER11 collet. I looked that up. That's 1/4 inch shank. That's the biggest tool you can get in there. 15K on the RPM. I had 140 inches a minute. It's programmable RPM, so you can spindle override or we'll put in whatever you want in there. About 140 inches a minute, your max. We also had to write a little bit of a post processor there because you can do a tool change with an M6 code, but it's going to try to go to a position and think you're going to manually change the tool. We like to run machines in single block. When you do that, it actually goes into a sub-program section, so we decided to take the M6 out to not have that happen. But we do everything on the setups as far as manual setups. Okay, we did download the whole model into our Fusion, and I did that to see how much room we had. And I also designed a fixture plate and thinking of like thin, long parts, and also anything you can put in a vise. We also got a couple of slim vices that were very narrow, and that worked out pretty well. We just added a couple more bolt holes through these 2 that we bought so it would line up with the T-slots in the table. Oh, also, you have to use 6mm T-nuts in these things. So I try to use 1/4 inch ones, and they don't quite fit. So, all right, we decided to do first project a Titan 1M made out of Delrin, and try to use one tool only, so we don't have to change anything. We do everything the same as Titan teaches us in his curriculum. We use Fusion 360, but you could use Mastercam. Really doesn't matter on this one. And here's a picture of every year we have. Every class makes a Titan 1M. We all take a picture with our new Titan 1M shirts. So Austin Dunk, the instructor over at Sarasota High, also made his Titan 1M. So we had to do our picture and send that out also. So right back there, we're able to make the part, no problem at all. Now on the Titan 1M, let me go back to the picture of the part. Of course, this vise was a little bit small. The long part of the vise is actually, that vise is actually in the VF2. I was testing it out before I brought it over, and I wanted to compare how each one cut. But in the VF2, I mean, in the DTM, I've been calling it, the desktop mill, it's longer in Y than it is in X, so you just want to be aware of that. I personally, I like that when I clamp on the vise, I like the vise to be facing me as far as the vise handle thing goes. It needs lighting inside. You want to probably put some like puck lights in there. It does not have an air blast, but we were able to cut no problem at all and not have anything clogged with the Delrin plastics. Mr. Dunk actually did another project on his own. We made this little coin out of plastics. I'm not sure what that is, but we have a lot of, we got acetal and PVC and all kinds of stuff we can cut. We could do woods, and we're probably thinking we could do thin sheet metal kind of projects. Like if you want to make parts that you got, like an assembly of a box or something like that. I know Mark McCullough has a lot of good CNC router projects that he's lent to me. So this is getting pretty long on this one, but very successful. It's just a matter of learning how do you do your setups. We just did a slightly, probably in edited post, and just be aware that it's only 140 inches a minute. So if your post is spitting out higher RPM inches per minute than that, you're going to get a warning that you're above the feed rate. So. But it's I think it's a very capable machine. I think the big plus is the Haas control, of course. Okay, talk to you later. Bye.
Wow, those are some really interesting projects. In fact, I learned a thing or two that I'm going to go back into the classroom in the fall and implement into some of my projects. And I'm sure you did as well. Now, I wanted to spend a minute here to say thank you to all the students and the educators who spent time creating videos for this project session. If it weren't for you, we wouldn't have had a session. So thank you so much. Now, I'm looking forward to being back in person in Tennessee in 2022 and having a project session in person. So if you're interested in helping plan that project session, please join the HTEC Council and get involved. That's all it takes, is just getting involved. Now, how you can actually join the HTEC Council is show up to the business meetings and participate, and nominate yourself this year as part of the HTEC Council. So definitely do that. And I look forward to seeing everybody in the business meetings at the HTEC conference. Have a great day.